Welcome, everyone. My name is Pam Pearson. I'm the director of the International Cryosphere Climate Initiative. And ICCI works to bring the latest science to policymakers and increasingly to the general public. So in that spirit, this presentation actually takes advantage of the presence of two leading scientists who spoke earlier today at the research dialogues, Dr. Chris Stokes, who will be addressing ice sheets, and we'll hear first from Dr. Harry Zekalari, who will speak on a recent study that came out in Glaciers. The thing that struck us about these two studies is that they were looking at what we're jokingly calling, but this is a serious issue, two sides of the same ice cube. In other words, they're looking at glaciers and they're looking at ice sheets, but they're finding strikingly similar results in terms of the thresholds for really what we have to call catastrophic loss being much lower than what was thought, even at the signing of the Paris Agreement 10 years ago this fall. And that leaves us with the same message that in a sense we're sleepwalking into what are really serious changes and a very different planet, as you'll hear. I need to emphasize that both of these are in essence consensus studies. The Glaciers study in particular is coming from a very large group of co-authors, and it will feed into the IPCC AR7 cycle. And the ice sheets paper has four very leading ice sheets experts who worked on AR6, on sea level rise and what we need to expect in coming years. So I'm going to turn to the presentations, and we'll do them consecutively and have time for questions afterwards. And this will be made available online, also on ICCI's website, as well as, of course, the UNFCCC website cached for those who are not able to catch this at the time that it is being shown. And please don't hesitate to reach out directly to us if you're interested in the slides or any other aspect of these presentations. So with no further ado, I'd like to invite Harry to come and operate his slides, speaking for Glacier MIP.
Thank you very much, Pam, and thanks for the introduction. I'm gonna try to put it in full screen. It pops up there. So hi, everyone. My name is Harry, and today I'll talk a few minutes about glaciers, why they matter, and why the situation is pretty grim, and why every 1/10 of a degree does matter for glaciers. If you ask someone, why do you care about a glacier, there's always gonna be different answers. If you live very close to a glacier, you may think of natural hazards. This is also what happens in Switzerland 2 weeks ago, where a glacier collapsed. On the more regional scale, glaciers are really important for water supply. When we think about high mountain Asia, it's about 2 billion people are really reliant on glaciers, on the water that they're providing. And then finally, the question that I often get as a glaciologist in Belgium is, why are you studying glaciers? And it's sea level rise, of course, and a lot of places on Earth far away from glaciers will also be impacted by how glaciers evolve. So we try to model their evolution. We try to make projections, as you can see in this little movie here, where you really see this is the iconic glacier. It's the Aletsch Glacier, the biggest glacier in the European Alps. It's about 20 kilometers in length. And you see the evolution under current emissions and under very low emissions. And what we then typically do is we don't only model one glacier, like you see here, but we really model thousands of glaciers together. And if you do this, you can make global assessments about how glaciers will evolve. And this is what you see in this image here. This is the evolution on long term of how glaciers will evolve. And what was really new about this study is that we didn't only look until 2100. So far, most studies, including those in IPCC and some that we conducted, they were always looking until 2100. But glaciers need a lot of time to respond. It's what you see on this figure. You see that the horizontal axis goes to 2,000 years. So it means that all the glaciers are already changing a lot now. The way that they will change is really going to be taking centuries. And so what you see here is that under a plus 1.5, which are the green lines, with plus 1.5 you lose about 50% of the mass. And with plus 2 the difference, well, there's a quite big difference between plus 1.5 and plus 2 degrees when it comes to the world's glaciers. Now, this is again, it's showing the same, but in a different way. On the horizontal axis is the temperature level we'll end up with. On the vertical axis is the amount of ice that will be remaining. And you, for instance, see that with current climatic conditions, and that's counting 1.2 degrees, that's the average temperature, the average increase compared to pre-industrial levels for 2014 to 2023, you see that today, under these climatic conditions, you lose 40%. So it means that without any additional warming, 40% of the glacier mass is committed to be lost. And then you also see that, of course, for higher warming levels, you'll be losing more. And you see that between plus 1.5 to plus 3 degrees, there's a sensitivity where every tenth of a degree will be causing 2% of additional global glacier loss. So these are the global numbers. And if we look into the regions, we'll see that, in fact, it's really different, and that there's some differences for the different regions. So I'd like to end by showing you this figure that I'm going to build up together with you, because it's a quite complex figure, but it's showing you the way that regions will respond in a different way to given today's warming levels and other warmer levels. So let's start by putting up, I typically call these pizzas or pies. The blue part is bad. It's the part of the pizza you don't want to eat. Well, in this case, it's the part that is lost. So if we look into the lower left corner, you see this is for the global. You see that globally, you remember I mentioned to you before, 40% is lost. So at 1.2 degree, 40% of the global glacier mass is lost. Then you can look into your region of interest, or for instance, let's look at the region which is here referred to as Central Europe, which are the European Alps. You see that in the European Alps, without any additional warming, eventually we'll be losing more than half of the mass in that region. And you see that some regions really stick out. The most dramatic one is Arctic Canada South. Arctic Canada South will lose about 80% of its volume, irrespective of any future warming. And this was really an eye-opener for us, because by 2100, so in the studies that we had in the IPCC reports until now, Arctic Canada South didn't look too bad. And the reason is because it needs a lot of time to respond. So by 2100, you don't really see the effects of current climate policies and, well, the levels we'll be going to. So this is the part that is lost in any case at 1.2. And then the message that I mentioned before, you see I'm going to be popping up some lines. Every line is a tenth of a degree, and then you see how much more you lose. So in the lower left corner, between plus 1.5 and plus 3 degrees, every line on average corresponds to about 2%. Every tenth of a degree globally will be leading to 2% additional loss. And you see that in some regions it's different. In some regions which are pretty well off, so what is well off? Look at regions where the blue part is small, for instance, South Asia West or Central Asia. These are good because good in the sense the committed loss is not that high, but these places are super sensitive to the future warming. So remember before I told you 2% additional loss per tenth of a degree? Well, in some regions, in these regions, it's the climate policies that matter even more. There is more than 3% per tenth of a degree, for instance, in these regions. So to kind of summarize that again, now in a table form, the names are a bit different. Before I was using the terminology that we use as glaciologists. This is a more general, I would say, terminology for the regions. What you see here are regions that even under temperatures lower than today, that's what you see here in the left column, under temperatures of today are lower, they'll be losing 50% of their mass. So in fact, it's a temperature that you need to only have 50% mass loss. And you see that in these regions, it looks very grim. With plus 3, barely anything remaining. If we would go to a plus 2 degree world, a bit remaining, but not that much. But the good news or message of hope is that if we're able to limit warming to 1.5 degree, it's not a lot, but there's still a part that can remain. Now there's other regions where the committed present day's loss is a bit less pronounced. And here you see that all of these regions, the temperature levels are higher than today. That's the temperature levels at which you lose about half of the mass. And these regions are the ones which I told before where the future warming will be really, really important. And you really see the big difference. In a plus 3 degree world, there's a bit remaining. In a plus 2 degree world, there's more remaining. With plus 1.5, there's a substantial, well, more than half of today's mass that will eventually remain. So these are the regions that will be most affected by climate policies. So very short wrap up. What to remember, 39% is committed to be lost at today's level, so irrespective of future warming. The actions that we undertake today, it's not a future, it's not a long-term problem. Like glaciers are already massively changing today. But on top of that, everything that we do today will not resonate only for children or grandchildren is really going to be for many, many generations. And this has huge implications for water security and also for sea level rise, as Professor Stokes will be explaining in the next talk. And there's a very large difference between plus 1.5 to plus 2 degrees. And the title of our paper, in fact, is, I would say, still a message of hope, is the fact that the glacier preservation can really be doubled if we're limiting the warming to 1.5 degree compared to plus 2.7. So remember the pizza that I showed to you before? Well, with plus 2.7, there's about 25% remaining, so about a quarter of the global glacier mass. On the other hand, with plus 1.5, we can still save more than half. So I think that's a message of hope. And I'd like to end with this. Thank you very much.
Thank you so much, Harry. So we're going to switch now to Professor Chris Stokes at Durham University. Harry, by the way, is at Virgin University, and if you would pronounce it properly for me for once.
Well, getting the mic on is difficult. It's a tricky one. It's the Vrije Universiteit Brussels, so the Free University of Brussels.
Thank you. And while the switch also takes place, I need to mention that this is very symbolic in many ways. This year is the International Year of Glaciers Preservation, approved by the UN General Assembly. But it's also the first year of the Decade of Action on Cryospheric Sciences. And so symbolic of that, in a way, we're moving from glaciers, which is this year, to an entire decade, which includes all cryosphere, including the great ice sheets, which have severe implications for sea level rise in particular. And Chris, I don't know if you include in this particular presentation how much sea level rise would occur if all the glaciers melt. Okay, it's a bit of a big difference. So please go ahead.
Thanks, Pam. Yes, that number, 65 meters of sea level rise is locked up in Greenland and Antarctica. Actually appears in my first bullet point on the next slide, but this was a paper that we published just a few weeks ago. There was a kind of sense that perhaps limiting warming to 1.5 will solve a lot of the problems in terms of climate impacts. But our clear conclusion from a kind of synthesis of all of the available evidence is that it's probably too high. In fact, I would say it's certainly too high for polar ice sheets. So my key conclusion in my first bullet point here is that limiting warming to 1.5 is essential, but it will not slow sea level rise from melting ice sheets, which, as I said, store around 65 meters of sea level equivalent. So even if they just lost 10% of their mass, just thinking back to Harry's talk there, even if they lost just 10% of their mass, that would be 6.5 meters of sea level rise. What we know is that even under current warming of 1.2 degrees, that sea level rise is accelerating. There's a recent paper published just a few months towards the end of last year showing that the rate of acceleration of sea level rise the rate of sea level rise has doubled. It's currently rising at 4.5 millimeters per year. But if we just take that current rate of acceleration throughout the rest of this century, then we reach rates of 1 centimeter per year before the end of this century. And as I said to my children back in Durham recently, they should keep hold of this paper and see if that is actually borne out within their lifetimes, because we often think of sea level rise as something very distant, something that's happening in the future. This is happening now, and the rates of acceleration are alarming. If we look back at what's contributed to sea level rise, thermal expansion of the ocean waters has been one of the dominant causes. The ocean warms and it expands. Melting of the smaller mountain glaciers and ice sheets has also dominated the contribution over the last few decades. But what we're seeing now is a quite dramatic decline in the ice sheets in Greenland and Antarctica. And they are now, for the first time in the last year or two, seem to have overtaken the mountain glaciers in terms of their sea level contribution. So if we look at this plot, this is a plot of satellite data that actually measures very accurately the mass gains and the mass losses of the ice sheet. So everything that you can see on this plot, the thin lines are the East Antarctic ice sheet in black, which actually stores over 50 meters of sea level equivalent. The West Antarctic ice sheet is the red line, and the Greenland ice sheet is in turquoise. And any of the line that's below the zero, the dashed line along the center of that plot, means it's contributing to sea level. You might notice that you can see for East Antarctica in the last couple of years, we had some very, very heavy snowfall events. That was misreported in the media as the Antarctic ice sheet growing, so I just want to correct that misconception. It's not growing. They were short-term weather events, but overall, the Antarctic contribution to sea level rise is certainly positive in terms of its adding to sea level rise. The most important line on this graph is actually the dark blue line, because that's the cumulative sea level rise that's been caused by the ice sheets over the last few decades. And you can see they've added nearly 25 millimeters to global mean sea level. They're actually adding about 370 billion tons of ice each year into the global oceans. So we looked in this paper at the current observations of mass balance, and it paints a very dramatic picture. Some of these rates of mass loss exceed what we thought was the worst case scenario just a few years ago. The other thing we did in this paper was we looked at how the ice sheets responded during past warm periods and what kinds of sea levels were attained. And what's very clear from this table, and I'll just zoom in on a couple of important numbers in a second, is that we should expect several meters of sea level rise over the coming centuries. It's very clear if you go back through the IPCC reports that, multiple meters, 2 to 9 meters, 5 to 9 meters is locked in already over millennial timescales. And we used to think that this would take 1,000, 2,000 years. We now know that that's almost certainly incorrect, and that things are happening far more quickly than previously thought. So just to highlight here, if we look at the forcings in the top row, the last time the Earth was kind of as warm as today, actually slightly cooler if you look at the numbers, then we got sea level rise of about 2 to 9 meters. And that's very worrying. That was obviously a natural warm period caused by the way the Earth orbits the sun. If we go back a bit further in time to about 400,000 years ago, we had another warm period. Again, CO2 levels much, much lower than present. Global mean temperatures between 1, possibly 2 degrees, and we get 6 to 13 meters of sea level rise. And then finally, if we go back to the mid-Pliocene, about 3 million years ago, those CO2 levels and the temperatures are very kind of comparable to where we might be going in the next century or so. And you can see there that global mean sea level is 10 to 20 meters high. This is not complicated science. This is very simple physics that if you warm planet Earth, you lose mass and you increase sea level. And actually, just as I was preparing the talk, a new paper came out in the last week or so showing what they did is they modeled the ice sheet over the last 800,000 years. And what was quite startling in these results was that it was very consistent with our message that actually current warming, perhaps a slight degree of ocean warming, just 1/4 of a degree above present, causes almost complete collapse of the West Antarctic ice sheet and generates about 4 meters of sea level rise. So when you run their animation, the black dot, the dots there on the blue line are showing you the ocean temperatures, and the 0 line is kind of present day. And so what you see as we hit those red circles is when the ocean just gets a little bit warmer than present. And you see complete collapse of the West Antarctic ice sheet, which as you look at it is on the left-hand side of the graph. So there's a really clear and consistent message from this study that if we hold current ocean conditions as they are or just increase them very slightly, we are committing ourselves to losing the West Antarctic ice sheet and adding about 4 meters to sea level rise. And this is very consistent behavior. And then finally, the third piece of evidence we looked at in this study was actually computer simulations of the future sea level contribution from both the ice sheets in Greenland and Antarctica. And most computer simulations show that 1.5 degree will not slow sea level rise. As I said at the very beginning, there's a sense sometimes that 1.5 will solve our problems, but that is not the case. With sea level rise from ice sheets, we are committing ourselves, even at current warming levels, to several meters of sea level rise relatively quickly. This plot is just from Antarctica. It shows what's possible just from Antarctica at a 1.5 degree scenario. We're looking at over 1.5 meters, that mid-range, the black line, over the next few centuries. And this is very, very concerning. There are other studies out there. There's a growing number of studies showing that current warming is sufficient to trigger collapse that is irreversible on human timescales. We can get rid of these ice sheets very quickly. It takes a much, much longer time to regrow them. So to finish, these are my conclusions. Limiting warming to 1.5 is essential. But the best case scenario is that sea level rise is slow and steady. And by that, I mean kind of less than 10 millimeters a year would be manageable potentially. If we exceed 10 millimeters per year, then I think that starts to become something that's very challenging to adapt to. And we know that ice sheets are losing mass at 1.2 degrees, which is where we are at the moment. and that actually we would hit that 10 millimetres a year before the end of this century. So every fraction of a degree really, really matters for ice sheets. Tiny change in temperature cause multi-metre increases in sea level. And to slow sea level rise from ice sheets to a manageable level requires a long-term temperature goal, clearly, that is closer to 1 degree, certainly has to be cooler than present. And so the sooner that we can slow and stop the warming, the easier it will be to return to those safe levels in the future. Thank you.
So I just wanted to add a couple of things. We can open it up for questions, but two. One is, right next door to us right now, actually the ocean dialogues are going on. And to some degree, they speak about sea level rise, but the sea level rise comes from glaciers and ice sheets. Similarly, when you think glaciers, think of downstream, think of water resources, think of what that ice serves. Because there is, I think, a sense that these are areas that are far away, that these are areas that don't have a lot of impact, that we can feel sorry for the people who live in these areas or the species that depend on them, but they're actually quite vital. If you look at the number of people who are at least seasonally dependent on water resources coming from glaciers and snowpack, you get up to about 3 billion, somewhere between 2 and 2.5 billion in the Asian region alone. The second thing is, however, that in this year where we heard this morning at the research dialogues from IPCC and WMO that, last year was 1.55 degrees. So we're over the 1.5 limit. But if you also look at the materials that the IPCC puts out, if we are able to reach net zero, if we are able to begin pulling carbon dioxide out of the atmosphere, but even without that, temperature actually begins to come down relatively quickly once we stop pouring greenhouse gases into the atmosphere. So it really remains up to us to take those actions. This is not please, the sky is falling, the ice is falling, right? This is really important to focus on as urgency and ambition and hope, and not just to give up. So to sort of wrap things up, I wanted to pass the word to Dr. James Kirkham, who is the AMI Chief Scientist. This is Ambition on Melting Ice, which is a group of countries that are both polar and mountain and downstream and low-lying, to give a few words, and then we can open up to questions if there is a bit of time left over.
Thank you very much for the chance to respond to those two both very powerful and important presentations, which have such important implications, not only for the radical need to shift ambition here in Bonn during these negotiations, but also for the pace of climate action globally. Now, many of us here on this panel were actually in Tajikistan last month for the high-level conference on glacier preservation. And in a keynote speech at that conference, COP29 President Babayev said some remarks which really stayed with me. And those were that the science has moved on since 2015, when the Paris temperature limits were negotiated. Now, the two studies which have just been presented here add to the growing mountain of evidence that even 1.5 degrees will not be sufficient to prevent irreversible and cascading global damage from the rapid melting of the Earth's cryosphere. That includes unprecedented loss and damage due to rising seas, salinization of coastal land, and also changes to water supply. But what is even more concerning is our current trajectory, because as you've just heard, continuing on our current pathway will destroy over 75% of the world's glacier ice. It will lock in potentially rapid sea level rise for centuries to come that will exceed the limits of adaptation, cause extensive loss and damage for centuries, and even cause loss of existence for some coastal communities. But the latest science also sends a strong message of hope. By achieving 1.5 degrees, we can save twice as much glacier ice globally compared to our current pathway, and we can keep the pace of sea level rise down to rates that coastal communities can adapt to. These are the stakes which are being negotiated here in Bonn these 2 weeks, and those stakes are incredibly high indeed. We are not just losing our glaciers, we're actively killing them. We're killing them through our collective lack of action, through the choices that delegates are making here in Bonn, through our inability to implement the steps and the measures that science has been calling for decades now. Distinguished delegates, the time frame for emissions reductions to preserve glaciers, ice sheets, and their vital ecosystem services is now extremely short. There is little room to course correct after 2030 because the pace of loss currently is so high. That is why it is absolutely essential that countries can deliver much more ambitious NDCs at COP30 so that we can begin to stabilise these accelerating ice losses and minimise their globally growing impacts. We have to fight now with renewed effort and urgency more than ever to prevent every 1/10 of a degree of warming, because every 1/10 of a degree matters for the preservation of glaciers and ice sheets globally. If we can achieve a low emissions pathway, we'll begin to see improvements in glacier stability in just a few decades, and that will send a clear message of hope as well as urgency. Thank you very much.
Thank you very much. We are now at the end of this press conference, but all of the speakers are available for questions afterwards. So thank you very much.